Alright, welcome back everybody. In this video we're going to look at the examples from the linearization lesson. We talk about what a linearization is, and you see this fancy formula here for what a linearization is. But if you really think about it, all this is it's the equation for a tangent line rearranged so that our y value is the only thing on the left-hand side, and that's the equation that we normally see for a linearization. All we've done is we've subtracted or added the minus f of a that appears on this side when we write the equation of a tangent line. And so that's really all we're going to do here. When we find a linearization, we're finding the tangent line to the function at a point. So let's look at example 1. We're going to find a linearization of the function y equals 2 sine of x plus x squared minus 5x at x equals 0. And so in order to find the tangent line, the first thing I need is a y-coordinate for my point. So I substitute 0 into the original function, and I get that the y-coordinate of the point is 0. So this is going through the point 0, 0. The other thing I need to do to write the equation of a tangent line is find the slope. In order to do that, I'm going to find the derivative and evaluate that at x equals 0. So the derivative for this function, dy dx, is equal to 2 cosine of x plus 2x minus 5. And if I evaluate that at 0, I get 2 times 1 plus 2 times 0 minus 5. It's going to be negative 3. And so my equation for my tangent line is going to be y minus the y-coordinate is equal to the slope times x minus the x-coordinate. And I get y equals negative 3x. Or if we wanted to write it in linearization form, L of x equals negative 3x. And now I'm going to use that to approximate the value of the function at x equals 0.3, and so I'm just going to substitute 0.3 in here for x, and my approximation is going to be negative 0.9. So there's my linearization, and there's the value at 0.3. Now, a question that frequently comes up with linearizations, how good of an approximation is this? And we'll talk about this more later, but how good of an approximation is this? What is the actual value of this function at 0.3? And it's negative 0.819 about. So that's a pretty decent approximation. Not super duper, but a pretty good approximation of the value of this. And the calculations to find the value from the linearization is significantly better than the calculations from the function. Alright, example 2. Choose a linearization for f of x equals square root of x in order to approximate the value of f of x at x equals 4.1. Choose a center of linearization that makes it easy to evaluate both the function and its derivative. I'm having a little trouble with my power cord, it appears right now. Alright, so we want a value of x that is close to 4.1. That if I substitute it into this function, it's going to be easy for us to calculate. Hopefully the obvious choice to you is 4, since we can very easily take the square root of 4. And so we're going to center a linearization around x equals 4. And so we substitute 4 into the original function, and we take the square root of 4, that's 2. So my point for my tangent line is 4, 2. Then I need the value of the derivative. If I take the derivative of this function, it's going to be 1 over 2 square root of x. And so f prime of 4 is equal to 1 over 2 root 4, or 1/4. Very easy to find. Now I write my tangent line, y minus 2 equals 1/4 times the quantity x minus 4. And if I rearrange it as a linearization, I've got L of x equals 2 plus 1/4 times the quantity x minus 4. And now I'm going to use this to approximate the value of f of x at x equals 4.1. We'll put 4.1 in here for x. And we get, let's see, 1/4 times 0.1, that's 0.025. And so my approximation at 4.1 is, is 2.025. Now, how good is that as an approximation? Well, we're approximating the square root of 4.1, which is, to 3 decimal places, 2.025. So the linearization does a really fantastic job of approximating the value here close to its center. All right. On to example 3. There's a little bit of narrative there from me as far as the usefulness of linearizations and limitations that we have. In example 3 here, we're going to find a linearization for this polynomial function, and then we're going to compare what we get with the linearization versus the actual value and look at the percent errors that occur. So first, let's go ahead and find the linearization. I find the coordinate, the y coordinate of my tangent line. I substitute 1 into this function. And if I do all the calculations for that, I get that the y coordinate is 5. And then I need the derivative. dy dx is equal to 3x squared plus 4x minus 3. And so dy dx at x equals 1 is going to be 3 plus 4 minus 3. That's going to be 4. And so to write my linearization, y minus the y coordinate of the point is equal to the slope times the quantity x minus the x coordinate. I add 5 to both sides. And there's my function for the linearization. So L of x is equal to 5 plus 4 times the quantity x minus 1. And now we're going to go about filling in this table. We're going to find the approximations for various x values. Alright, if I substitute 1.01 in here, I get that my approximation is 5.04. If I substitute 1.05 in here, I get that my approximation is 5.20. And all I'm doing is taking 5 plus 4 times the quantity and substituting these quantities in here for x and doing the calculations. It's 1.1, that's going to be 5.4. If it's 1.5, 0.5 times 4 is 2, that's going to approximate it at 7. And if I put 5 in there, let's see, 4 times 4 is 16, plus 5 is 21. Alright, now let's find the actual value of the function at these points. So to help me here, I'm going to just put this into my table function. And we gave us an easy to work with table here, or an easy to work with values here, and an easy to work with function, so that I could show you the concept that, not all approximations with a linearization are created the same. Just substituting those values into our original function. Alright, and so at 1.01 the actual value is 5.040501, and then it's 5.212625, and then it's 5.451 and 8.375 and 165. And now we're going to calculate the percent errors of these. And so for the first one, we've got 5.040501 minus 5.04, and we'll divide that by 5.040501 and multiply it by 100. And my percent error is 0.00994%. Very accurate, very close to the center. Alright, next we'll do 5.212625 minus 5.2 divided by 5.212625. And we get I forgot to multiply that by 100. And the percent error is 0.242%. Again, very good. You'd be very happy with a 0.24% error in an approximation. 5.451 minus 5.4 divided by 5.451 times 100. We get 0.936% error. So all the way out to 1.1, this linearization is providing an approximation with less than a 1% error. But as we get further away from the center, the error gets larger and larger, 16.418% error all the way out at 1.5. And so you see, as we move away from the center, you see that how drastically the error increases. And then the last one here is going to be pretty ridiculous. We have an 87.273% error. So what does this illustrate to us? It illustrates to us that very close to the center, the linearization does a great job of approximating. You know, for these values within 1/10 of where we have our linearization set up, we get less than a 1% error. As we move out, the error starts to grow, and as we get really far, like out here at 5, the error is at a completely unacceptable level for an approximation. So this is what makes linearizations useful. If we're calculating values of something, a lot of values that are really close to a particular area, we can come up with a simpler function, the linearization, that close to that value we have very small errors, but the calculations are significantly easier. And that's kind of the whole point of using a linearization, is we want to make our calculations significantly simpler, but also maintain some level of accuracy. And so they're really useful when we're making a lot, or evaluating this function a lot, really close to where we establish our center of linearization. Alright, that's the end of this video. See you guys next time. Have a great rest of your day.